All right. 6:07. Let's get started. I can see where we are waiting a lot more people join. You guys are welcome to the call. Tato, uh, I see Nohan, I see Salim, Tato, Ima, you're welcome. Yoba, you're welcome. Welcome to the call, guys. All right, so today, before I get started, let someone just remind us what uh, what topic we did last week. Yoba, can you help us with that? Ah, taking a feedback, then audio back. Who else is not hearing me? Please indicate in the chat. If you can't hear me clearly, just indicate in the chat, please. Keep tracking. 4, 3, 4. Hello, guys. Hello, everyone. Can you hear me now? All right. All right. Thank you. Thank you. All right. So I was asking, what did we do last week? Like the topic you guys just finished. I believe it was handled by Mr. Dixon. So we saw a quick refresh. All right. DG, please forgive me. I couldn't pronounce the first part of your name. You can go on, please.
Yeah, so we did the regression. We did regression. Then towards the end, we went to multivariable regression. I think like when there are two or more dependent variables. And then, yeah, so yes, two or more features that we are comparing against the target variable. But it was mainly regression that we did. We found n square error, we found r squared, and for there was a data set that we used. That was what we did last week.
Okay. 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 And I love to be intentional about what we learn. So I'm gonna engage you with a few questions. Mr. Deji, can you hear me?
Yes, I can hear you.
All right. So firstly, I heard you say multiple regression. Like you mentioned two features. Can you take that again, please?
Okay, so he said, I think if I can recall, he said there are some times where we are
Okay.
comparing, maybe for example, we are comparing two features. Hello, can you hear me?
Yes, I'm with you. Just go on.
Yeah, he said sometimes when you're comparing two features against a target variable, maybe there are many influences, there are many factors that influence your target variable. For example, maybe what predicts what is maybe the crop yield production. Like for example, the crop yield production, there might be many factors that maybe that might influence the continuous variable. What we are getting the output, it might be rainfall, it might be sunshine, it might be a lot of things. So if you want to actually get a more like accurate you want to predict the variable, you should not just compare one quantity against the other quantity. We should be comparing multiple quantities. So by that, we'll be able to be more accurate in predicting our variables. So multi-regression is I think you are comparing two variables, you are combining them into one, then comparing them against the target variable, as against just doing one feature against one target X onto Y.
Okay, but I think you have the idea, but there's some substantial argument you're missing from your definition. Okay,
Okay.
so okay, let me be sure you actually get everything. Like, can you give me an example? Like, uh, give me an example of a data set and what you'll be trying to predict, given the situation is a multiple regression.
Okay. Um, for example, right now, if you want to predict like maybe the sales price of the house, right? Maybe you want to predict how much a house is going to cost. There are so many factors that
Okay.
you will consider. You consider like the age of the house, like how old the house has been, the square
Yeah.
footage, like how big it is. You consider like the
Okay.
location. Sometimes maybe if the island is on the mainland, it's going to be more expensive. You consider like in the number of the bedrooms, a lot of things. That is so those things, right? They actually add up to how much the house is going to be. So if you are doing that, you need multiple regression or maybe for simple logistic regression, something that is only just one factor that influences the target variable, like what you are predicting.
Okay.
For example, I'm trying to
Okay.
see maybe like x equals to y. Maybe it's very linear, like it's a linear data
Uh,
set that once one is increasing, the other has to increase, and the other features don't really influence the feature like the target variable that much. That's when it's just single. But for multiple regression, it's like there are so many independent variables that will actually make or mar what you are going to have or what you are predicting.
all right. Beautiful. Thank you very much. Thank you very much. It's clear now. Okay. So not you, but I'm going to pick someone else before we get on with what we have today. Danny, can you hear me? Danny Fries. Please indicate if you can hear me. Hello, Danny. Or Hikma.
Hello, sir.
All right. Thank you, Hikma. So I know you guys did supervised learning last week.
Yeah.
Can you just summarize? Can you just summarize what supervised learning is? You can tell us how you understand supervised learning.
So from what I understand from supervised learning is training some data sets. You train it understand from the data sets, it gets trained and understand, okay, this and this makes the target variable. So you give it independent variable for it to learn, you allow it to learn, and then you now test it on data it has not seen. So most of the times when we're giving data sets, we share them into training sets and test sets. So allow it to learn with the training sets, then the test set now is what we use to test it and compare to the real values that we have. So we have the y predict, what the model predicted, and then what we have before. So now from there we get our, if it's for classification, we get our accuracy, our recall and precisions. But if it's for regression, we get our mean absolute error or mean squared error.
Okay, okay. Yes, yes, yes. This reminds me of something I was listening from the first speaker's explanation. Mean squared error and the likes of it. Now, I want to be sure we know why we calculate those. I'm gonna bring on someone else. Sigma, thank you very much for your explanation. Esther, can you hear me? Hello, Esther. Okay, Chuku. Hi, okay, Chuku. Can you hear me? Victor, are you there? Uh, why isn't anybody coming on? Zenandi, Zenandi, please forgive me if I can't catch the correct pronunciation. Please come up, Zenandi. Zenandi, can you hear me? Ah, Mr. Deji, are you still there?
Yes, I'm still here. I'm still here.
Okay,
I can hear loud and
some other people. Christopher, Christopher, you want to speak? Victor, please mute your mic. Please mute your mic. Oh, Victor. All right, thank you, Victor. Christopher, I thought you wanted to say something. Uh, why is everyone here? All right, Mr. Deji, let's just finalize this so that we move on. About regression metrics, you mentioned, and Hakim also touched that. You mentioned the likes of what's it called? Mean squared error. Exactly. Like, why do you calculate mean squared error? Your training.
Okay, yeah. So we calculate mean square error because we want to, after we make our predictions, right? We want to see how close like our predictions were to the actual value. So we want to see so that we can actually tell how accurate our values are. For example, let me say if you're having maybe if you're having 220 as the actual target variable, right? The actual value is
Okay.
220, and maybe our predicted is about 500. It means that the model is not actually predicting. It's not like it's very far from it. So those like so when we square the value of the when we square the difference between our predicted and the actual, we can able to actually tell how close our regression line, how the model is actually close to predicting the actual variable. So this helps us to know how accurate our model is. So if we are having predictions that are closer to the actual values, it means that our mean square error will be, I think, almost, it will be lesser than our mean, like the mean of the target variable. But if it's very, very, very far, it means our model is not actually doing very, very well. So that's the key metric for predicting our performance for regression model.
All right, that's good. Thank you very much. I'm going to add to what Strategy has mentioned. So, yes, he's right. Because remember, guys, we are dealing with machines. So, you can't trust them enough to be very, very much accurate, like to be exact or whatever we want to predict. You understand? That's why if you get employed as a machine learning engineer in the future, the company doesn't expect that whatever whatever you do have one or two prediction tasks or projects to work on. Your output will be very accurate, like it will be exactly as the future is supposed to be. So that's why we need evaluation metrics like regression, like yes, like mean squared error, for instance. So this is just to check how far or how close we are to the actual situation during testing and training. So that makes this evaluation stage a very vital step. Yes, a very vital step in machine learning. So that's it for supervised learning. Today we'll be touching on unsupervised learning. So Today will be more like an introduction into supervised learning. Then the next class will see how far and how quickly we can round up things on unsupervised learning. So let's get started. Well, I believe some of us might have checked on what supervised learning is. Like supervised learning, I don't expect that the idea about unsupervised learning should be far from our thoughts. So I'm just guessing that we already have an idea of what unsupervised learning is, a general overview of what it is. So Esther, hello Esther. All right, thank you,
All right.
Ibrahim. Please. Yeah, Ibrahim, you can go on, please.
Okay, unsupervised learning, unlike supervised learning, is another type of machine learning where you use data sets that don't have features already defined.
Features already defined. Okay. You still want to go on, or are you done?
I'm done, I'm done.
All right. So what do you mean by features? I also heard Mr. David using features. I want to be sure we use feature correctly because they have uh, they have an intentional meaning. So what do you mean by features, please?
Okay, sorry, I meant labels, labels.
Okay, labels, labels. All right.
Yes.
So so what you mean is unsupervised learning doesn't use labels to train the models, right?
Yes.
All right, that's great. Very much correct. Who else have a newer or a different explanation where you can indicate, please? Who else? Rabi. Yeah, Rabi, please go on. Okay, Hikma, you raised your hand.
Yes.
Yes.
All right, go on,
All
Hikma.
right. Go on, Tikma.
The
The
unsupervised
unsupervised
learning.
learning.
Uh,
So the unsupervised learning is where
okay,
this time around, instead of giving training the data training the model with your data set, it is just fed with the data set and allowed to train by itself. It trains itself based on what is given. So you look at it, and then the main type we use is clusters. So it clusters this data. You looking at it, learns by itself. We don't train it with any data sets.
okay. All right. That's great. Thank you very much. All right. So, you guys have said all there is in summary about unsupervised learning. Now, a closer look into what unsupervised learning is it learns from data. You have a model that learns from data without labels. Fine. But now, for the model to learn from this unlabeled data, you have to use an algorithm. And the same applies to supervised learning. As you know, there are various algorithms you can use in supervised learning. If you remember, okay, Mr. Didi mentioned linear regression already. This is one algorithm. There is logistic regression and the likes of it. So the same applies to unsupervised learning. There must be an algorithm because it's this algorithm, this model in this situation to learn patterns within data, because what the model does during unsupervised learning is to learn patterns and relationships within this data. That's how it can be able to make you understand, make groupings of this data. Because in most cases, like Hakim just mentioned, yes, that's Hakim. Hakim just mentioned clustering. So that brings us to the concept. If we look around, anytime you hear about machine learning does this, machine learning does that. There are three major situations you can find machine learning operating. One, it is that it wants to predict, that is prediction, or it wants to classify, which is classification, and thirdly, it wants to cluster. I hope you guys can hear me. Please, if you can hear me, just make some reactions. All right, thank you very much. So three things: clustering, predictions, and classification. Classification and prediction falls under supervised learning, while clustering falls under unsupervised learning. Thank you guys for the reactions. So in unsupervised learning, what you'll be doing majorly is clustering, and there are algorithms to help us reach this end goal. Example of these algorithms are k-means, popularly known as k-means clustering. There is hierarchical clustering. Can you guys hear me? All right. There is DB scan. These are three popular clustering algorithms you can find in unsupervised learning. And now, I don't like engaging technical concepts like this without practical situations. Now, I want to walk us through practical situations you can find unsupervised learning on the fly, like in practice, so that it doesn't sound like it's just a concept. We find ourselves having data sets, training. At the end of the day, we see clusters. Like, what are the practical use cases? All right, we will be touching that now. So for unsupervised learning, practical cases you can find the applications of this type of learning is customer segmentation. Now, I'll give you an instance. Amazon, for example, I believe we all know the popular Amazon. Amazon, let's say during the summer or during the festive period, Amazon can decide that Hakim, for instance, our machine learning engineer. So we'll be giving you a data set of our customers on labeled. We don't have any target variable, there's no prediction, there's no classification. Just all you have to do is get these data sets, find the relationship within customers, group them into clusters, and we create a marketing campaign for them. So Hakim will get the data sets, clean, do the necessary process, and maybe she decides to use k-means clustering, and there you go, there are clusters. Now within these clusters, now you can either find this algorithm grouping customers with certain characteristics. Maybe it group customers with by purchasing power and demographics. Yes, we can use that. You can group customers by demographics or yes, and purchasing power. And at the end of the day, you get different sections of these customers. Maybe you can get high ticket customers, low ticket customers, and mid range. And there you go, you have the template for market outreach. Now, Amazon will know that, okay, these high ticket customers, these are the kind of product we should advertise more to them. We can go ahead confidently showcase what's it called? high ticket products to these high ticket clients. And the same goes for mid range products and low range products to the low ticket customers. Please, do you understand all I've been explaining so far? Mr. Deji, please indicate if you understand. All right, all right. Thank you, Ibrahim. Everyone else, please, you can raise your hand if you don't get all I've been explaining earlier or so far. Okay, I'll assume we are all good with the explanation so far. Thank you. So moving on, there are more real world applications of unsupervised learning. Let me use to all our music lovers in the room. Let me use Spotify for instance. Now, have we ever thought about how Spotify can be able to recommend songs to us or Netflix or Spotify? Like how you can be listening to one of your favorite songs by, let's say, Davido, for instance, and the next song you have that plays on is something along that vibe. You understand? You don't get the video playing, and the next song that plays is in gospel music, for instance, like something out of the same genre. You understand? Well, guys, don't be surprised. Unsupervised learning might be in play under the hood. Now, what could happen in that situation is the data set can be given to Mr. Deji, the machine learning engineer for Spotify, and they say, Mr. Deji, we want to be able to recommend songs that align with what the customer starts with on our app. So they gave Mr. Deji a data set. What would Mr. Deji do? He selects an algorithm for use and he passed this data set through an algorithm. Let's say Mr. Deji hopes to use DB scan and it trains this model with DB scan algorithm. And yeah, they are now the model is now able to come up with clusters or relationships of songs with likely characteristics that once a song in that particular cluster is played, the algorithm makes sure that it recommends the same music in that same cluster. Both this is making sense. Hello, everyone. Please indicate if I'm making sense so far.
Sorry, Paul, your voice sounds a bit muffled. We're not hearing you clearly. I think we stopped that. I stopped hearing you clearly at Spotify. What is my
Spotify,
network?
right?
Yeah, when you're explaining Netflix and Spotify.
Sorry about that. Sorry about that. Is it better now?
Yes, it
Okay.
is. It's better.
Okay. But who else I could head past where Mr. Emmanuel said he wasn't hearing anymore? Hickman, please indicate if you stop hearing at Spotify as well.
I stopped hearing around where you said the algorithm they'll use to classify the Spotify songs that listeners that will be recommended to listeners.
Okay, okay, okay. Mr. Deji, how about you?
Yeah, that's exactly what I heard too. The recommendation system, the one you were saying about Spotify predicting based on your listening habits.
Okay, okay. I'm glad it's better now. I will go right again. But before I go on, I heard someone asking, Akachi, Akachi, are you there?
Yes, I am.
Okay, you were asking a question if it's the TA taking us. Yes, I'm the TA for today. And why are you asking? I don't know if it's because you're hearing my voice for the first time, but why are you asking?
Yes, that's part of the reason. Good evening, sir. We have been speaking by, I think, Sapong so far. So, first of all, when
Okay.
I joined, there was no one sharing a screen, so I didn't know if it was
Okay.
just
All right.
we students talking to ourselves.
Okay. I'm going to share my screen. So you're welcome to the call, and no problem. Thank you for the clarifications. Yes. So I don't know if Mr. Dixon mentioned this. You have we for the machine learning track we have like three teaching assistants so far. So yeah, so you from time to time you see us shuffling our roles, and um last week Mr. Dixon closed on supervised learning with you guys. So today I'm starting unsupervised learning, and it will be more of an introduction. And yes, I'll definitely get to share my screen shortly too. So you're welcome. Okay.
Yes, thank you. I was just clarifying. Thank you.
All right, no problem. I hope you can still hear me so I can go on with the explanation. Please indicate if you can still hear me clearly. All right, thank you very much. So, so like I was explaining, for for unsupervised learning, there are practical applications to this. First, I talked about customer segmentation, like one of the real world application you can use unsupervised learning for, and another is Netflix and Spotify, because if if you're to be given a data set as a machine learning engineer for Spotify or Netflix recommend content that are similar to what you're watching or what you're listening to on the app via unsupervised learning. There are situations where other concepts can be used, but this is a practical application where unsupervised learning can shine. Permit me to use that word. So in this situation now, you're given a data set, and this data set now contains a list of all the music or playlist or songs that are available on the Spotify service. So what you can do with this data set is to pass the data set via a machine learning algorithm, an unsupervised machine learning algorithm specifically. There are three popular, like I mentioned, K-means clustering, DB-scan, and hierarchical clustering. You can choose to pick DB-scan, and with DB-scan, you create clusters. So what the engine does, the recommendation engine does is, once you're listening to a song like Whiskey, a song from Whiskey, which is an Afrobeat, and what your these clusters, how these clusters are utilized is, Whiskey is in a particular cluster that has certain features. So as Whiskey is in play, the system makes sure that only songs from that particular cluster, because of course the algorithm have made a cluster from the relationship or groupings, let's say similar relationship within these songs. So that's how you can be able to recommend that after Whiskey, it gets to play one Afrobeat to another without breaking the flow of the vibe or the genre. I believe we all got this. Please indicate if you got this. All right, thank you very much. So I'll be quickly sharing my screen so that we can. Can you guys see my screen? All right, thank you very much. Is anyone that have already started this, that have started taking the unsupervised learning course already? Please indicate if you have. Manuela's the okay, it was assigned to us. All right, I like this. I like this. So that means I expect this to be a very interactive class. Hope you can still see my screen. All right, thank you. Trying to find the okay. So I'll be using the slides for us. We'll be going through the slides for practice. All right, unsupervised learning. As we already discussed, unsupervised learning finds patterns in data, clustering customers by their purchases. And if you can remember, I somehow touched this example, this practical use case, when I gave some real world applications of unsupervised learning. So it goes by compressing the data using, for this customer case, compressing the data using purchase patterns and dimension reduction. Do we know what dimension reduction is? Please, who know what dimension reduction is? All right, Mr. DG.
Okay. So dimensional reduction is, for example, let me say you have like a 6-dimensional data. You have data that has 6 features, that you
Okay.
have 6 features explaining the data, and some features
Okay.
out of it, they are just like redundant. They are saying the same thing. For example, height and weight
Okay.
is basically saying the same thing inside. So you want to pick the most features that explain more about the data, then you want to cluster it based on that data. So maybe if you're reducing like a dimension of a data set from maybe 12 to like 3, the best 3 that explain the like the variance in the data, that's dimension reduction, so that you can be able to tell the story and you can be able to yeah, out of it.
All right. All right. Yes, that's dimension reduction. And he also touched about the reason why we engage dimension reduction in our machine learning. Because as he rightly said, some of these features are just not necessary. So that's why you always have to monitor for too many features. There's this concept, there's this word I'm trying to, yes, the cost of dimensionality. That's the word I'm trying to remember. So now this cost of dimensionality means you have a data set where there are just too many features, like features are just so much. Either um, features made during your analysis, because sometimes there are certain techniques you might involve during machine learning and you end up having more features. Like for a case of encoding, encoding using dummy pattern to encode our data sets. Hope I'm not touching a feature that's too technical. Please indicate if you know what encoding is. Let me see if I have to go back and talk about it. Mr. Deji only. Okay, Mr. Akachi, Mr. Ibrahim, thank you. All right, for the rest of us all right, Akim, I see you. Samuel. All right, for those of us who don't know what encoding is now encoding is a concept that is very, very much vital to machines for them to learn. I will say two things. Machines are dumb and smart. Now, if you have a data set you're training a machine on and you have some features, let's say some features you have a data set where a column is for salaries and another column is for age. And you know the max age anybody can ever attain is well, I can't determine how long someone can live, but let's say 120 years. Okay. Then for salaries, you can have salaries like outrageous numbers for salaries. You can have the salary such as oh, I have a call. Sorry guys, sorry about that. All right, labor and coding. All right, so you have the salary with an outrageous number of oh no. Oh, sorry guys. I was talking about standard scaling. I'm very, very sorry. Apologies. So label scaling is about attributing numbers to categorical columns or features of our data set. I'm sorry, please forgive me. So label encoding is a situation where you have, let's say you have a feature that has different possible kinds of values you can attain. Let's say you have a feature where what can I use now? Okay, you have a feature where school, for instance, academic school. Let's say you have a data set for people, and you have a column that talks about the school they attend. Is it school or certification? Is it that they have attained the BSc, they've attained a master's, or the so far they've attained secondary school or WIC certificates for West Africa? So now what you can do for that, you can't just pass that column to the machine like that. It won't know what to do with it. So what you can do there is you encode these features. You attribute groupings to these values. Secondary school, you can say 0 means secondary school, 1 means BSc, and 3 means masters. This is the best way your machine can understand that, oh, okay, these are numbers. These are what I understand. It doesn't understand Bachelor of Science. It doesn't understand Masters of, the BS, the Masters full, the full meaning for Masters. Machine doesn't understand all that. What they want to see are numbers. What machines always want to see are numbers. So that's why we have to encode them. So that's it for what label encoding is. And yeah, so there are certain features like that that when you try to encode, you end up having a lot of features. Yes, because there are certain technique you want to encode with, because there are different kinds of encoding pattern. There's one hot encoding, there's label encoding, yeah, and there's the use of uh, dummy method with pandas. And those situations now you find out that you'll be creating a lot of features for your data set. So that's where dimension reduction can help a lot. Alex, Blessing, you guys didn't raise your hand during when I asked about encoding. I hope we get it now. Esther as well, Emmanuel, please indicate if you get the explanation for encoding. All right. Thank you very much. All right. So moving forward, we have a data set, Iris data set, for instance, and they've given us a little heads up that this dataset contains measurements of many iris plants. So there are 3 species of this iris datasets. There is Etosa, there is versicolor, and there is virginica. These are the 3 species we have on this iris datasets. Now, the features available on this dataset, features or columns, I'll be using them interchangeably. Please, let's be aware. This data set now has, this iris data set will be working with has a peta length, has peta width, has sepal length, and sepal width. So now, with this data set now, we are expected to pass this or train this on an unsupervised learning algorithm. And we would want, what would be the outcome of this now? We want this algorithm to be able to make clusters for these species. So just assume that at first, this machine doesn't know the species that are available. It just has this This is what all the machine has to work with: peta length, peta width, sepal length, and sepal width, and that's all. So this data set is a 2D NumPy array. It has columns, which are the measurements, like I mentioned, features, which is used interchangeably with columns. And each rows indicates each iris plant. So this data set was taken, for instance, let's say we have a group of people going from one plant to another. For this plant, they take peta width, they take a peta length rather measurement, they take peta width measurement, they take the sepal length and sepal width, and they record it. That's how they went on doing for a number of plants. So this number of plants are the rows we have on this data set. Now, this iris data is 4-dimensional. Now, 4-dimensional means it has 4 features, 4 columns. So that means if this data set was to have just 3 features here or 3 columns, we would end up saying the iris data is 3-dimensional. Please indicate if you understand so far. If we are following, thank you very much, Alex. Thank you, Manuel. Thank you, guys. So, all right, dimension is equals to number of features. Yes, we get that. Dimension too high to visualize. Yes. So there is a concept. Has anyone here ever tried to plot a 2-dimensional data set? Please indicate if you have. Anyone? All right, Akachi. All right. Okay, so how about plotting more than 2? Okay, okay. Now we hit a roadblock whenever we try to. Of course, you can plot this, but there is this complexity that comes with trying to visualize more a dimensional space that is greater than 2. There is a complexity because in this case, you're dealing with trying to visualize a pattern where you have 4 features at the same time, if it's a 4-dimensional. But in the case of 2-dimensional, you can just say, okay, I want to plot what's it called, a line graph, for instance, or yes, a line. Yes, you can use a line graph. You want to plot a line graph, for instance, for a cases where you have an x variable and a y variable. Now, trying to include another feature into this becomes more complex. So that's why here it is indicated that the dimension becomes too high to visualize because it is more than 2. It is more than 2 in this case. But in this case, we don't have to worry about this because unsupervised learning will give us insight into this higher dimensional space. Now, as I touched earlier, there are popular algorithms you can employ whenever you want to do unsupervised learning. One is k-means clustering. It is very popular among the others. And for k-means clustering, the algorithm is very interesting and very simple. But in general, it tries to find clusters of samples. It tries to find clusters of samples. So how does it do this? How does this k-means algorithm do this? But I will leave the floor to maybe someone want to try to explain how k-means algorithm can help with clustering. Mr. Tatu, can you hear me? Okay, let's do it this way. Please just raise your hand if you want to take the floor. It's an open floor, please. If you want to attempt and tell us how k-means help in clustering. Anyone? Anybody? All right, Hakeem, thank you very much. Please go on.
So the K means clustering. It clusters based on centroid. So it looks for a centroid. So when you give it the number of clusters, you have to impute the number of clusters you want. So let's say for instance you choose 3 clusters. So now it
Okay.
finds the centroid for each cluster, and then the data points it calculates the features. Those closer to each centroid will be a cluster. So if you have 3 clusters, each cluster we have a centroid, so the features that are closer to that centroid will be with it, and then you use like a visualization color scatter plots points to show colors, maybe red showing okay this cluster could mean one type of the Irish sample, then the other cluster will also mean the other Irish sample, and then the third cluster, something like that.
All right. You do have the idea. Thank you very, very much. I appreciate. Anyone else? Anyone wants to add to what Hakeem has explained? All right, Mr. DG, please go on.
Okay, so at the beginning, it asks you when you initialize your k-means clustering, you
Okay.
are to input your number of clusters. So when you
Okay.
input your number of clusters, right? So if you, for example, if you are
Mhm.
picking n equals to 3 as your clusters, it randomly assigns 3 centroids to the
Okay.
visualization chart. So when it does
Okay.
that, right? So every data point that is closer, so it looks at there's like a algorithm that picks the closest to the closest to the centroid has like a cluster. So what it does is then it now goes on to calculate the mean of the data points, like the mean of each cluster. So it's constantly like
Okay.
reassigns their clusters. So the mean of the cluster, when it does that, it shifts the centroid to a newer distance. Like so, the actual mean of the cluster is shifting the centroid to that place. That is the new assignment of the centroid. So it keeps doing that and doing that and doing that. So when it does that, some clusters that were initially assigned as a cluster, if they are now closer to a different centroid, they'll be assigned to another cluster. So it keeps doing that until there's a time where the centroids can no longer shift again. So it continues to do that until the maximum number of iterations are reached and no more no more clusters are made anymore. So that is the final clusters that will be assigned to each of the data points.
Okay. Okay. Thank you very much. Hakeem and Mr. DG, yes, you guys have touched more than enough about how the algorithm works. And I would encourage us to always understand how each algorithms for each learning goes by, each machine learning, like how they operate under the hood. This gives you a more understanding, and it in most cases it helps you to be able to pick the perfect algorithms for certain situations that you encounter. So in addition to what Mr. Kim and Mr. Deji has explained, there is also a concept employed. Apart from picking a centroid and finding the mean and gathering uh, data points that are close to this centroid, some other concept that occurs is calculation of distance. Now, when centroids are being initialized, as they've explained, there is a pattern to calculate this distance. Like to be able to calculate, okay, for this centroid in this space, this centroid, this centroid in this space can be able to look and say, hey, this data point is close to me. So this makes part of my own cluster, because at the end of the day, that centroid will become a cluster. So, but how does it do this calculation almost accurately? There are certain ways this distance calculation can be done. One is Euclidean distance calculation, and it is mostly used. Euclidean distance calculation. Please indicate if you guys can hear me. All right, now with this Euclidean distance calculation, this is how centroids can be able to know that that data points are the ones closer to me, so that we can form a cluster at the end of the day. Now, let's move forward. Now, in order to use this clustering algorithm, one has to pick the number of clusters that would be used. Like, number of clusters must be specified. But some cases, this is the drawback of k-means clustering. I'll explain later how this is the drawback. Like why indicating the number of clusters is a drawback. I will get to explain this later. And k-means clustering can be accessed. This algorithm can be accessed via sklearn, which is popularly known as scikit-learn. It's a Python package that was developed by some genius in the tech space. Shout out to them. And from this package, you can be able to access k-means clustering algorithm to be able to work with. So now, practically, these are the samples you're given, the iris datasets. From sklearn.cluster, you can be able to access k-means, like I mentioned. So from sklearn.cluster, you import k-means algorithm, and you initialize the model with this. Model equals to k-means. In bracket, you indicate the number of clusters. In this case, 3 number of clusters was indicated. And the next stage is you fit this model with the samples. These samples here you have to work with. This one here. You fit it with these samples. And the next following is you call the predict method to the sample, which is saved as labels. Because at the end of the day, we want to be able to make clusters. And these clusters are, in this case, are called labels. That is, what are the clusters? Like, categorize these clusters. What are the labels? And your output here, when you print them, are numbers. Now, these numbers are unique. The unique numbers here are 0, 1, and 2. In this case, that means the first data point has been assigned to cluster number 0. The next one falls under 0. The next one, 1, 1, 1, 2. And like that. There you go. Clusters have been made. 3 in total. 0, 1, 2. That makes up 3 clusters. Please indicate if you understand and you can hear me. All right. Is anyone having challenges so far? Please raise your hand so that we can go back and explain better. Anybody doesn't seem to understand? All right, Blessing, thank you very much. Yeah, Blessing. Okay. I thought Blessing raised her hand. All right, so I assume we are good so far. Okay. All right. So now with this algorithm that we've been able to use to predict or cluster this sample, we can go on to add new samples to the existing clusters. And with what the machine has already learned or clustered, you can be able to say, okay, you look similar to cluster 0, come to cluster 0. Or you look similar to cluster 1, come to cluster 1. And like that. So k-means, after training and creating clusters of centroids, if the algorithm always, and this is very vital, it always needs to remember the mean of each cluster, because this is how it can be able to assign a cluster, sorry, to be able to assign a data point to itself to form a cluster. Because it is through this mean point or this centroid, it can be able to check the distance of the new added data point. It will check the distance of this data point from itself. Let's say now we have three centroids that have been made: centroid 0, centroid 1, and centroid 2. All centroids would look, is this data point, using that Euclidean concept I mentioned, is this new data point close to me? If yes, then it is part of my own cluster. This is how further clustering can be made using the same algorithm. Now, just imagine a situation where k-means doesn't remember the mean of each cluster it has already been trained on. Let's say after training this k-means on this iris data set, the next time you try to cluster a new data point or some set of data points, it forgets. What would happen? What would happen? Let's take a wild guess. What would happen? Yeah, guys, please save us. Toba, quite a lot of people I haven't heard their voices so far tonight or this evening. I just hope we are following up. Mr. Emmanuel, can you take a wild guess? All right, please take a wild guess. If after training this k-means algorithm, then it tends to forget the mean of this cluster, what do you think would happen? Please, we want to hear your voice. Just take a wild guess. Or maybe someone else.
I think he finds the, I don't know, nearest closest. I'm sorry, I'm just taking a wild guess here. I got distracted for a bit.
Okay, should I go over the question again?
Yes, please.
Okay. So now, yeah, it was mentioned that k-means remembers, and I mentioned that it is very vital that k-means algorithm must remember the mean of each cluster. It is very vital. So remember, just imagine a case where it doesn't remember at all. What would be the fate of our algorithm? What do you think would happen?
I mean, it's not going to be accurate if it doesn't remember that the centroids or the means, as you said. I don't think that the results will be accurate or reliable.
Oh, yes, yes, yes. Thank you very much. That is very much true. Very much true. Akachi, do you want to go? Anything for us?
Okay, sir. I was going to say that
Okay.
if the model doesn't remember
Okay.
the clusters, it means that whenever we have a new data point
Mm,
added to the data set, the centroid of one or more clusters could shift or change. So basically, it may mean that our model is not learning from the training data. And then whenever you have test data, it tries to predict afresh. So
okay.
it would also mean that your model is not reproducible. You can't use it in you can't vouch for your model basically in other use cases.
Yeah. All right. Right. Thank you very much. Those two explanations are very, very correct. It could go two ways. As Mr. Emmanuel mentioned, it's misclusters. Permit me to use that word. It ends up clustering situations that are unreal or that are not true. Then secondly, it can end up going over what it has already done before, meaning it is not reproducible. And I can add to that one of the backlogs it will end up producing is time, time specs. So that means anytime we get to add a new data set, the model has to go back, train from the beginning, test, and that's a lot of time. We don't have this much time doing production, like doing real world use cases. So these are the three cases. These are the three situations that can end up if this algorithm tends to forget the mean of each cluster. Okay, so Yes, it finds the nearest centroid to each new sample. Yes, like I mentioned, each centroid looks at the new data point and say, okay, using Euclidean distance measurement, is this data point close to me? Fine, it is. I take you in. You are now a part of my cluster. All right. So this is a situation where we have new samples for the existing algorithm. So the new samples is passed on the predict method for our same model. If we remember, this is the model we initialize here. This is it. Model equals to k-means cluster n equals to true. Then we fit. This model is now ready for new predictions. Like after this test, if this was to be our test sample, for instance. So the new the new sample is passed on the predict method, and there you go. It's able to predict these labels. So that means in this case, we had 3 data points, and it was able to check to get the first data point classified to centroid 0, centroid 2, and centroid 1, or we can say cluster 0, cluster 2, and cluster 1. So that means in this situation, like I mentioned, these new data points, the centroids looked at each other and say, okay, centroid 0 saw that the distance from the new data point to itself is much closer than any other centroid. It classified it to itself. The same happened to 2, and the same happened to 1. So now there are situations where you can use a plot to visualize what has been going on under the hood. This is a scatter plot, okay, that can be done using matplotlib.pyplot. Now, in this situation, we are visualizing, we have a scatter plot of the sepal length of these samples, the sepal length plotted against the beta length. Like each of them, you plot the sepal length versus the beta length. Now, each point you see here on this scatter plot, each point represents an iris sample or an iris plant that have been measured. Now, the color on this point indicates the cluster it has been assigned to. Let me zoom in, and we can see these are 3 different colors. This happens to be somehow dark blue. This looks something light green, and this set above looks brownish, if I'm correct. Yes. Sorry, guys. This looks all right. This looks brownish. Now, this is now visualizing the labels we've been able to come up with and the existing data set. So what I've been done here is we got the labels, which is the third, which is the third feature. For instance, the third feature on this data set. We plot the sepal length, the beta length, then we assign each of their labels to it. Let me give us an example so that it doesn't sound complex. Now, for these 3 data sets, for instance, that have been that have been clustered, we can get these data points. These are the new labels. These are the clusters that have been assigned. Get from the data set, get their sepal length and their petal length. We plot a scatter plot for the sepal length versus the petal length. Then assign this 0 to 1. Assign each of these by color to it. That's how you can get this. This is how we are coming up with this. So this color now, with this algorithm now, with this package now, yes, this Python package, pyplot, we are able to assign colors to indicate, hey, this data point belongs to this cluster. So that's where you have 3 different colors there. I just hope I'm not sounding too complex. Please, anyone indicate if it's getting blurry, if the explanation is getting too blurred or vague. Okay, you can leave a reaction if everything seems clear. All right. Thank you, guys. Thank you very much. So this is what I've gone under the hood here. So with this visualization, we can be able to attain that, okay, fine, we have to be clusters. And this is how they've been clustered so far. So let's go back to our real world use cases. Let's say now this was our customer segmentation and not Iris data set, for instance. Now let's use our customer segmentation. We had some a data set of a list of customers. So at the end of the day, we can say, okay, the algorithm was able to cluster this into three, as we indicated. This upper set could be the set of people who patronize our high ticket products, or this here can be the low or the mid, depending what the depending what the classification was based on. The relationship was used to classify this. All right. So this is what I've gone under the hood. This is the practical code implementation of how we were able to come up with this. From the scatter plots, for the scatter plots, you import this library, this popular Python package, matplotlib.pyplots, and you import as PLT. Now, these XS samples, this is called Python, this is called slicing. Now we are trying to extract a particular column from the data set, the Iris data set. And if you remember, we extracted only two. We had 4 dimensions or 4 features of 4 columns. Out of these 4, we extracted sepal length and petal length. And here they are. XS equals to samples. We extracted the sepal length, yes, and for Y, we extracted the petal length. And now we plotted, we made a scatter plot using this, using this this code, this scatter method from pyplots, plt.scatter. It's a method available for us to be able to plot a scatter plot. So you pass the xx, which is the x axis, and pass the ys. Then you indicate C, which is equals to the labels we were able to come up with, like the labels that have been produced after using our k-means clustering algorithm. Now these labels were able to indicate the colors. I didn't think C was not here. You will just see these data points would not be plotted without colors. They would not have a uniform color. Let's say they would have all been black. You understand? But these C labels was able to tell us the groupings or the clusters that were created during our training using the k-means algorithm. And of course, we use plt.show to be able to see what have been made so far. All right. So let's move on further to evaluating a cluster. And this is where we would round up for tonight. First of all, why do we have to evaluate a cluster? This should be a very cheap. It should be a cheap answer, because during our throwback on supervised learning, we touched something similar to this. Like, why are we evaluating our cluster? Why don't just after you train, you test, and that's it? We go on to use this algorithm, this train algorithm. Mr. Ibrahim, can you tell us why we have to evaluate our cluster? Why we have to evaluate what have been made so far? The answer is even on the answer is already on the screen itself, but let's just hear. Mr. Ibrahim seems he's not here. Mba, are you there? Tatu, I'd love to hear your voice, Tatu. Zenandi, can you help us, please, Zenandi? Oh, come on, guys. I would really love to hear your voice. All right. Deborah, are you there? Deborah. Ah, it's just unfortunate. All right, Ibrahim, please help us. Thank you.
Okay, so
Mm,
um, it helps us to know whether the clusters we found are useful, meaningful, or
okay.
insightful to what we are looking for.
Mm, okay.
Yeah,
That's
unlike in
mm,
supervised learning,
mm,
unsupervised learning does not have labels which we can use to compare
okay.
whether the results we found are correct.
Okay.
So this
Mm,
helps us to find out whether what we found or the clusters we have are useful and
okay.
meaningful.
Yes.
Yeah.
All right. All right. That's very much true. Thank you very much. Thank you very much, Ibrahim. Yes. So we definitely have to find because guys, some of the use cases of machine learning could be critical, could be a critical use case. Just imagine you're trying to cluster you work in a hospital and you're trying to cluster patients, you understand? You don't want to make mistakes, you understand? You have to try to be as near accurate as you could be. Because what what if this your task or your project you're working on could save someone's life or get the case worse. You understand? So you should be able to make sure that confidently this algorithm can do well. So that's why we have to evaluate our clusters and in general evaluate machine learning algorithms. So evaluating a cluster, you check the correspondence. Now there's two situations where you can evaluate a cluster. You can either evaluate when you have, but this is not mostly the use case. Real world can always be different. In a real world situation, you won't find this favor. Now, it's a favor about where you have the data set and you also have their labels. I know it sounds funny, but yes, but this only happens during practice because this is the situation where this is one of the situations we have here. Checking the correspondence with the iris species. And also a situation where you don't, the second situation is where you don't have these labels. I know it's supposed to be unsupervised, but now you're training the model on without the labels. At the end of the day, you want to be sure, can I trust this? After after the labels have been predicted or made, these clusters have been made from your algorithm. You try to compare it with the clusters that are real that have been available to check if it is good, but it's not always the use. It's not always the situation because in real world use cases, you won't have any labels. So now we are evaluating to measure the quality of the cluster, like Mr. Ibrahim has helped us mention. It informs the choice of how many clusters to look for. Yes, we will come to this. Yes, we will come to this. Now, one of the cases we can evaluate a cluster now from our practical use case for the iris datasets, K-means was able to find three clusters among the iris samples. Now, do the clusters correspond to the species? That's the question. That's why we have this table right here. This is called cross tabulation. Now we're able to check like how confident was this labels? Is it that we have labels classified into two clusters at the same time, or we have some labels classified into the three uh, uh, clusters at the same time? So that's what we have here. Now, this means for labels 0, 1, and 2, this row means during clustering, the accuracy for cluster 0 was that out of during this clustering, 2 were not well classified, meaning they were either for versicolor or they were either for Virginica. While for cluster 1, there was a confident cluster, meaning this cluster is very accurate so far for our training data set. The same goes for 2. It means our cluster wasn't really accurate. It wasn't really accurate. Like the accuracy was not as cluster 1. So far, 1 was the most accurate classification or clustering we came up with. And like I mentioned, this was done using cross tabulation with pandas. Cross tabulation is a feature or a package or method. I'm trying to find. Okay, yes, we'll come to that to make sure these frames has that. Now, the clusters versus species is that we saw here is a cross tabulation. It is accessed using the pandas library. Now, given the species of each sample as a list species, that's how we were able to do a cross tabulation. Now, this is the practical uses where you can evaluate. Now, you import pandas as PD, you create a data frame using the labels on one side, like creating the labels for a column, then having the species on one other column or feature. As you can see here, the first data point here was classified under cluster 1, which is a Setosa species. The same for the next, while the other was vesicular, and so on. So the cross tab of labels and species that we saw earlier was done using this code implementation. This is the syntax. Yes, this is the syntax that we use to come about this evaluation. Now, measuring cluster quality using only samples and their cluster labels, which we just did. This is the use case we just checked for now. And now there are some concepts to put in mind. A good clustering should have tight clusters. Now, this means that samples in each cluster should be bunched together. What this means is, we remember, for this case now, there were 3 centroids. We want to be able that at the end of the day, this cluster, okay, we could be able to say that this cluster or this clustering that have been made so far are very confident because each of the data points that were assigned to these clusters are close to them. That's what tight means, meaning that each of the samples or data points around these centroids are very much close because there are situations where these data points are not close, but they have been classified to this. These are the situations where we have this, where we have that means in this situation now for row 2, for this 2 now for special 2, the situation here was that there were data points they were assumed to be closer to vesicolor and at the same time close to virginica. That's why we don't have a confidence clustering for special 2 and 0 because of this situation. Hope we still understand. Please indicate thumbs up if we still get the explanation so far. And if we are missing out, please indicate. You can raise your hand so we can go back and make more clarifications on it. All right, nobody. All right, we'll move on. This is 7:30, okay? We'll just close up with this concept. Inertia. Inertia means clustering quality. Now, what inertia tends to do is it helps us measure how spread out the clusters are. And there's an indication here, lower is better. Of course, I will explain this. After fits, like after running the fits, there is a method there's an attribute we can always access, which is called inertia. And that is what have been done here. After initializing your model and you fit it to the samples, this inertia is an attribute we can always access. And the inertia tends to tell us how spread out the clusters are from each other. Now, this diagram will help us explain this better. There are a number of clusters that have been made, or should I say there are a number of possible clusters we can always pick. But there is a problem to this. If you remember, I talked about this. That one of the setbacks of k-means clustering is that we always have to choose a clustering in the number of clusters that we hope to achieve. Now, this is the problem, because the question is how do we know the right amount of cluster to pick? How do we know so? What if at the end of the day, the possible number of clusters that we can get from the data set is more than 3, it's more than 4, or it's 2, or it's more than 4? So yeah, it's more than 4, 5 as the use case may be. How do we know that? That's where the setback of this k-means clustering algorithm comes in. Now, how do we deal with this? How do we deal with this? We can do this, we can take care of this by using the inertia that we mentioned here. You can know the right amount of clusters to pick using an inertia. Now, we are going to explain. I'll come back to this frame where we have this diagram. Let's see how it was implemented. Just hope this frame wasn't able to pick it, unfortunately. Okay. So what has been done here, let me try to explain. Next week, we'll have a practical run through on how we'll see how this can be implemented using the codes. But now let me just attempt an explanation. Hopefully we'll get it. So now what happens here is a range of clusters. What happens in this situation is a range of clusters are picked. Let's say instead of initializing 3, a range of clusters will be passed to this variable here, number of clusters. So in this situation, we'll have, hope we can see where I'm at. Model equals to k-means, n clusters equals to 3. Now for this situation, instead of just passing 3, we can pass a list of this number of clusters. Here we can have 1, 2, 4. Let's say a range from 1 to 6. You understand? Now from this 1 to 6, we want to be sure which of this number of
Hello guys, can you still hear me? Yeah, sorry about that. My other device. I don't know what happened to my laptop. It just fizzed out. Sorry about that, guys. So, as I was explaining before that happened, what we try to do here now to control that setback is we pass a range of clusters. So we don't run an assumption that this data set has to be 3 clusters. You understand? So after doing that, there are certain code implementation we do. Now, what this code implementation does is it helps us generate inertias for all this number of clusters for the models we'll be training on. And that's how we get this graph we have here. And it is popularly known as the elbow method. What this elbow method does is that it tends to show us the number of clusters that is accurate to train this model on. So let me zoom in a little bit. Hope you can see my screen. Please thumbs up if you can see my screen. Thank you very much. So what this idea does is it tends to show us the number of clusters that is very accurate for this algorithm. As we can see, on the y-axis, we have the inertias. This is equal to the inertia for each cluster we pass. You know, we are not just passing 3. We are passing a range of clusters. Yes, number of clusters that we hope to use. In this case, 1 to 10. That is, we have cluster number 1 that we are passing, that the number of clusters will be either 1, 2, 3, 4, 5, 6, 7 until 10. And for each of these clusters, these are their inertias. The inertias are plotted on the y side. Now, when we plot this, we can be able to see which of these is the accurate number of clusters. And how do we know that? Where the graph tends to fall. As you can see, this is the point from which the graph slopes. Let me use that word. Or it tends to become stunts. 3. I'm circling 3. So with this graph now, we are able to see that, oh, yes, at this point, this is where we can make a decision that the number of clusters that is accurate to be used is 3. Please indicate if you understand. Thumbs up, please. If you still understand, thank you very much. Anyone indicate if you don't understand so far, you can raise your hand so that we can explain better. Okay, nobody. All right. So that's it. So these are situations where we don't have to run on assumption that, oh, these data sets, let's just do a guesswork. The number of clusters is, let's use 2, let's use 3, when that might not be the case, because you might end up choosing the number of clusters to be 4, when it could be no more than 4. The right cluster could be more than 4, could be numbered, or could be more than 6, depending on what you pick to be the number of clusters. Okay, yes. How many clusters to choose? It was mentioned. A good clustering has tight clusters, yes, that we've mentioned. So low inertia. And yes, that means if we look at this graph here, you will see that the inertia that have been chosen is not the highest. Remember, this line, this Y graph, is where we have the inertia indication. And if we check, the cluster didn't fall on the highest or the set of high ranges. Instead, it was somehow in between, not too low, not too high. So this elbow method is a method I encourage everyone to always employ, because I've seen situations where some engineers just go on, they're dealing with k-means clustering, and they just, they create clusters and they assign a number to it that, okay, this should be the number of clusters. No, that's very, very wrong. It is very, very wrong. So, as we mentioned, this situation is an elbow. You can see the reason why it is called an elbow is because if we look now, this graph, this line now resembles an extended elbow. If we look clearly, you see it resembles an extended elbow. So that's why it is called an elbow method. If you have a different data set and you tend to plot this inertia against the number of clusters you want to pick from, you will always have this particular picture, this look. You always have this elbow resembling graph. That's why it is called an elbow method. And if you see now, we picked the inertia where we picked the number of clusters where the inertia begins to decrease more slowly, which is this 3, from this point 3. So at the end of the day, for this IV's data set, which was used for this situation as this use case, 3, which is where the inertia begins to decrease slowly, is the good choice for a number of clusters. Yeah, so we've come to the end of the class today, and I hope everyone was able to catch all that have been discussed. Tato, you keep giving me a hands up, but I do want to hear your voice. Tato, can you just at least tell us you understand what have been explained so far?
Yes, I understand. I understand.
All right, thank you very much, Tato. Thank
Thank you
you.
for the session, sir.
All right, thank you for coming up. I appreciate. I appreciate. Yeah, I appreciate. Oh yes, Deborah, attendance. Thank you for bringing that to my attention. Yeah. Thank you for bringing that to my attention. There should be a form, but let me do this old school. I'll be taking a screenshot of everyone in attendance. Okay. Yes. Thank you. Thank you, Deborah, for that reminder. But I don't want to believe that everyone understood all that have been mentioned. I don't want to assume. Please, I encourage questions. If there's any place you missed it out, please just indicate. Raise your hand so that we can go back and we can work together. Anyone, please, anywhere you need clarifications. Is it when we talked about the practical? Okay, Deborah. Thank you very much, Deborah. Please ask a
Good evening, sir. Sir, can you hear me?
Yes, I can hear you now. Please
Okay,
go
good
on.
evening, sir.
Yeah, good evening to you.
Okay, just that I'm having challenge
Okay.
in this learning track, understanding it.
All right.
Why
What is it
why
exactly?
the after listening to the classes on data camp, watching the video, I'm
Okay.
not being able to do the exercises.
Okay.
So that because this is my first training. I've not had any training on tech, so I don't know. Does it have to
Okay.
do with pre-knowledge of data analysis and Python? So that I'm very confused to
Oh,
be sincere.
okay.
I
Oh,
want to
wow.
know
Wow.
if I'm really on the
Mm.
right track, if I need to go back to the data analysis or if I have to change. So it's
Okay.
a bit confusing for me.
Okay. Now, the first question I'll ask you, Deborah, is you you did wanted to learn machine learning. You did wanted to learn machine learning from start, right? Like from the onset, you set up your mind that you love machine learning and this is what you want to do. Is that true or
Yeah.
incorrect?
Yes, sir. Yes, sir.
Okay. All right. And prior to this decision, do you have any knowledge in data analysis in the past or data science?
No, sir.
Okay. Wow. Yeah, that might be a bit of a challenge, but there are two things I would say concerning this is that if you can put in the right amount of sacrifice or time, you can be able to catch up. You can learn whatever concept you don't seem to understand because some concepts that are used in machine learning are always comes from the roots because the root there is data science. Data analysis is there, but data science very important because a situation of we are talking about yes, playing around with pandas library, for instance. Data science touches this, which is data wrangling or data manipulation. It's a principal concept that is found in data science, but you can still pick up if you have the right grit. If you put in the right grit and amount of energy, you will definitely pick up. But if if you think like you might have to still touch the basics in place, then uh I believe you're on the WhatsApp, the general WhatsApp group chat. You can just say hi to me or indicate yourself, and we can discuss this so that we can find a solution to this problem. All right. So you're not left behind at the end of the day. Okay.
No, sir, I'm not on any WhatsApp group. Oh. This is Discord. But I'm not even on the Discord
Okay. Yes.
AI
Discord is
platform,
better.
sir.
Okay. You're not on the Discord platform.
The one I'm seeing is data science. I'm not on I've been clicking. It's not taking me to AI and machine learning track.
All right. I will leave my number on the general chat. I will leave my number. Please kindly say hi on WhatsApp, and I'll add you to those groups. I don't know how to quickly fetch those links. I would have just pasted them. Or if anyone can get the links for the Discord, you can just paste as well. But meanwhile, here's my number, Deborah, or maybe anyone who might have similar challenge. That's my number. Just say hi on WhatsApp, and I'll definitely respond.
I
All
appreciate,
right,
sir.
Deborah. All right, no problem. And yeah, some other people are raising up. Ibrahim, all right, Ibrahim, please go on.
Okay, so I just wanted a little clarification on the inertia that you just mentioned.
Okay,
Is
clarification
inertia,
on.
yeah, is inertia the measure of how tightly the clusters are to each other, or the data points in that particular cluster, how close they are to each other?
Thank you very much. Thank you. And yes, apologies. I mentioned that I was going to talk well on inertia. Thank you for bringing that to my notice. Now, everyone, this is what inertia means. This is a broken down explanation of what inertia means. It is actually calculating the distance of each data point to the nearest centroid. That's what it means. So inertia tends to measure how well the clusters are formed, because with the close with how closer these data points are to the centroid, it indicates how well this cluster will be formed. Because a good cluster means each data point closer to it are each data points assigned to it are very much close to it. So there are situations where this closeness is it's not correct, or should I say it's too spread out. It's not really that close. So that's where inertia comes in. It tells us, okay, on average, all the clusters that have been created or grouped, this is how well the distance is from each centroid to the data points. I don't know if this answers your question, Mr. Ibrahim.
Yes, it does. Thank you. But the graph you used was indicating otherwise. Like I was thinking it was the distance between clusters themselves,
No.
not the
This
data
graph,
points.
okay. Can you still see my screen?
Yes, I can.
All right. Now, this graph wasn't to show us, like you just mentioned, this graph, the purpose of this graph now is to tell us the right amount of clusters we should pick when training our model. If you remember, when we want to initialize our k-means model, we have to indicate the number of clusters. If you look very well, where is that? It's right up here. I think we're close. Here you go. Can you see this, Ibrahim? K means n clusters equals to 3.
Yes, I can.
All right. Now, as I mentioned, this isn't a good practice to just go ahead and just pick a number of clusters. Like, what if the correct number of clusters is supposed to be more than 3? So that's why we are using this graph. That's why we are using this graph. Next week, like I said, we'll see a code implementation on how to get this. But this graph now is to help us tell us that the number of clusters that is accurate to pick for these situations is 3. And it is plotted using the inertia of our algorithm on different number of clusters. Because if you were to train this cluster now, let's say separately, just have an idea that we use 1 as a number of cluster to train a K-means algorithm. We come separately, pick another the same algorithm and trained on 2 number of clusters. That. For each of these algorithms, we can be able to access the inertias of these algorithms, these separate models. That is what we have on the y-axis. Now we brought together all these inertias and plotted them against the number of clusters we use to get these models in order to get the right idea of the number of clusters that is appropriate to use. I don't know if that's answered your question, Mr. Ibrahim. All right.
It does, sir. Thank you.
All right. So, Odimayo, please, what's your question? You can go on.
Okay, thank you. Not really a question,
Okay.
but seems you've answered. I have not been able to join the AIML Discord group.
Okay.
And I spoke with the other TA last week, but he didn't respond. So I've chatted you now. Thank you.
Okay, no problem. Okay, you're welcome. All right, Toba, you can go. Yeah, Doba.
Hello,
Barry.
sir.
All right, good evening, Doba. Thank you for coming up. Yeah,
Sir.
what's your question, please?
Okay. The first question I have is, after we are done with, okay, let me start like this. When will they give us a task to do for let me say for a week? Why is it that if somebody finished the particular day that is the deadline, they are saying is late? And secondly, once we are done with what they give us for that week, can we still continue, or we have to wait for a new task to assign to us? And the training you did today, can you like send a recording of it? Because my phone sound is actually very low and my laptop is dead, so I have to like revisit it because I'm not following the screen and everything. I need to revisit it for me to be able to get it right.
All right, no problem.
Today.
Okay, is that all?
Yes, that's all I want to say.
All right, for the third question, yes, you get the recording for today. Then for the first question, yes, you complained that sometimes the assignments, even after submitting, it says you're too late, right? Is that a question?
Yes, you're late. Like if, let me say for example, my last week task was to end on the 13th. I finished the second one on the 13th. I finished the first one before 13. Then the second one I finished it on the 13th. They said that it's late and it's supposed to finish that day 13th.
Okay, but what was this particular assignment? What was the assignment in question? What were you meant to do? Hello, Doba.
Sorry, I don't know, my mic is muted already. I said the course we told is not assignment, the course track to cover for the week. The regression, that was what I finished on 13th.
Okay. Are you sure? Because I want to assume that it's not an issue from DataCamp, but it could be maybe a glitch or something. But are you sure you were able to complete the course, like section for section, everything will have been completed, and the whole course turned green, like the course you were supposed to complete before the date?
Yes, I completed everything. I did everything.
Okay.
I did it, and the second one, that's the only what they said that is late. I finished that one exactly 13th.
All right,
I finished
no problem.
I finished on the 13th in the afternoon, and once I check my app, the notification, they said I completed it late. So I don't know why it's like that.
And the assignment was supposed to be submitted on 13th, right?
I didn't hear you. What did you say?
Was the assignment meant to be submitted on the 13th?
Yes, the course track supposed to like they assigned to me, so I supposed to complete it on the 13th.
Okay. I think you were a little bit late. So it could be that let's say on the 13th now, that the 13th counted from 11, no, sharp 12 o'clock on the same day. So I believe submitting after 12 o'clock is late. I don't know if you understand.
That
Toba.
submitting in the afternoon, like from 12 p.m. is late.
No, 12 at night, like when the start of that new day counts. Do you understand now?
I'm not still getting it right because I finished it around 3 p.m. in the afternoon on the 13th. That one when I completed the second task.
Yeah, that might be the issue. You are quite late because if they say the deadline is 13th, maybe the system calculated the deadline to be from the starting hour of the new day, which is always 12 a.m. Do you understand now? But
Yeah.
meanwhile, okay, but
No,
meanwhile,
sorry to interrupt. Yeah, because
okay,
the time showed 00 hour.
maybe that
13
was
zero
how
zero. Mm.
okay, maybe that was how the calculation was made. But regardless, if does anyone have a similar situation to this, you can just indicate with a thumbs up, just a thumbs up. Let me see. Anyone faced similar challenge? Okay, no problem. Anyway, just Doba, just my advice, Deborah. Okay, no problem. So what our advice is, let's just try to submit before the due date. Like if it's supposed to be 10th, try and submit before 9 or 9. Just try that way so that you won't be caught in the loop of when the time is calculated on how late it is on that particular day. Then you ask a second question, Doba. Please remind me. I don't know if we've touched all.
Second question is since on the 13th, no, the first week when we started our track, the first week they assigned us when we are done, they assigned the second one. Then after the second track, the regression, they've not assigned anything, and I don't know if I should continue to study. I don't know what is the plan. What is it like so I can know what to do because I've just been doing practice. I've not like continue with the track.
Okay, is this your first breakout session so far? Like since joining the program?
No, this is not my first breakout session. This should be
Okay, that
my
means we're part of the
third
supervised learning trainings.
in the supervisor training.
Yes, supervised sessions. You were there, right?
I was there, yes.
Okay, all right, no problem. Now, this is what I'll advise everyone. If you're done with a particular course or assignment that have been assigned to you, please move on. Don't wait. Just move on. Now, the reason why I will encourage you to move on is this helps you be introduced to the concept or whatever topic will be touched early. And while touching it, you can be able to note down questions in a particular direction that you can ask to aid your understanding. Maybe when having a breakout session like this, you can, if the explanation so far doesn't answer the question you have in mind or you've noted down from personal studies, you can go ahead to ask, you understand? And that serves you better. And I also encourage us that sometimes if what you're going through, like doing personal studies, you don't seem to get some of these things on Datacom clearly, you can reach out to on that's why we have a Discord group. You can just put it out there. Let's talk. We don't mind if you're going further than everyone else. Maybe someone might be taking the same path with you, or a teaching assistant might be available to just help you out, and you're moving at a good pace, if I should put it that way. You understand? Are you with me, Doba?
Yes, I'm with you.
Yes. So hope I've answered your question.
Yes, you have. Thank you, sir.
All right, you're welcome. All right, Amosu Oluwafemi, please come up. What's your question? Then finally, we take a question from Mr. Deji. Yeah, Mr. David, are you there? Your hand is raised up. Okay, maybe
Hello.
David is.
Hello, I'm there.
All right, Mr.
Okay.
David, go on, please.
Okay, so it's about what we did today in class. I wanted to ask, because I noticed that we were using clustering on just two features, X and Y for scatter plots. I wanted to ask, does k-means really work well on a data that has that is multi-dimensional, that has a lot of features? Like, does it really work on? And if it doesn't, are the other methods for unsupervised learning the cure to k-means, or the one that actually builds up on k-means? And I also wanted to ask, does it also work well on categorical data? Like, is it just numerical data that k-means works on? And if it does, how efficient is it? That's my question. Those are my questions.
All right, you've asked two questions so far. I'll answer the first one, and you remind me of the second rather. Now, the first question you're asking is, does k-means do better with high dimensional data, right?
Yes. That's my first question.
All right. The base answer is no, really. It's no. It doesn't perform well in high dimension. Now, this is the reason. Remember, I mentioned something like because of dimensionality. Can you remember?
Yes, I remember that.
Yes. Now, there are certain algorithms. We have a lot of algorithms to train machines on. There are some algorithms that tend to fail, or they don't do better when the features are so much. And k-means is one of them. But there are still helping hands you can give to these algorithms. How? Reduce dimensions. There are concepts to do this. There's PCA, which is a principal component analysis. This is one way you can help reduce the cost of dimensionality to help this algorithm do better. But by default, k-means doesn't do better with high features. I believe that answers your question.
Yes, it does. Then the second one is for categorical data. Does it also work well on categorical data? Because I was trying to picture in my head, the mean of the centroid, and in my head it was all numbers and numbers it looks at. So does this really work efficiently on categorical data, and is it as efficient as how it would be if the old data sets, all these features are just numeric data points?
Yes. It does well on categorical data set as well. Let me bring you to something now. You see this sepal length and this thing that were mentioned here. Do you know that it's possibly this data set from onset was captured as categories? I can give you a situation. Let's say the sepal length now is 2.5 centimeter. And Peter length 1.2 centimeter. Now, if that was the particular way this length or these measurements were captured on our data, those are categories at the initial state. Maybe during cleaning, the machine learning engineer was able to clean this and remove CM from it. Do you understand, Mr. Deji?
Yes, I do.
Yes, that is a situation. Apart from other categories, possible categories we can use k-means on. So that might have been the situation. And remember that at the end of the day, we can't just, even if you have a categorical data set or a data set that has categorical features, you can't just pass them like that. Remember we mentioned encoding. Do you remember now?
Yes, we did. Yes, I remember now.
Yes, so at the end of the day, we have to pass numbers to the machine. They don't understand those words, you understand? But those encoded numbers represent these categories. You understand now?
Yes, I do. Yes.
All right. I believe the question is answered. If not, you can still tell me about it.
Yeah, it is. Thank you very much.
All right. You're welcome, sir. Okay, seems There is no more questions so far. Anyone? Any question? There are a lot of people I would have loved to hear from them this evening, but maybe next week. Maybe next week. All right. Okay. David is back. All right, Mr. David, let's hear from you. Hello, David. I don't know if it is network. David, are you trying to say something?
Can you hear me?
Yes, I can hear you now.
So I said whenever I'm at the data camp front page, and I always get notification on the right hand side that I have assignments. But whenever I click them, take me anywhere. And also I've made numerous complaints, and I'm told I should go through the group, and I don't even get any group tab on my page. I'm just
Sorry,
confused.
please, can you just repeat the question again? I'm
I
sorry, please
said
go over your question.
that on the data camp page.
Okay. I don't know if it's me. David seems to be
Section in
breaking.
the left hand side that says continue where you left off on the course. Can you hear me?
Okay, continue where you left off from the course. All right, you stopped at continue where you left off. I'm with you.
So on the left hand side of the page,
he keeps getting worse. Yeah, Mr. David. David, please just the network though it's not stable from your end. Just kindly drop a message on the group chat. Drop your question on the group chat. Network seems to be bad.
Okay.
All right.
Okay.
All right. So while we are waiting for
I'm not on the call, so
yeah. You're not what?
Hello?
Yes. I say you can just drop your message on the chat so that we can respond to it. Or you can reach out to me on WhatsApp if any way that looks better for you. It's 10 so that we can close the meeting for today. Mr. David, just reach out to me on WhatsApp, okay? Mr. David, just give me a thumbs up if you. All right. You got that. All right. So no question for today. So this will be all. Mr. Deji, before you left, I saw you raising your hand, but I want to assume all is well. So.
Yeah, I just had one more question, but I don't know. It's not
Okay.
okay. The question is that in that example, right? We had
All right.
species already. I think
we
because
had
in my
what?
mind,
Sorry?
I thought like, yes. Hello, can you hear me?
Yes, I'm with you, please.
Yes, when we're doing that cross tabbing, I noticed that
Okay.
the species, I think the species column was like was like a label already. So it's already telling us, okay, because you said we should always have to like evaluate our key means to see how accurate or how how it classifies it. So what if our data set does not even have something to cross-check it with? What if what it only has was features and we want to actually check how accurate it is with the actual for that like the species now? I think there was like a versicolor, the 3
Yeah,
hours. That was like the target that showed us
yeah,
how close
yeah.
it is to. But what if our data set does not even have something like that? How do we evaluate?
Thank you very much. That's a very, very good question. I'm conscious of time. I don't know if anyone would want to try this question. It's a very important question. Hakim has left. Anybody wants to go for this question before I say something about it? Anybody here? All right. All right. No problem. So to answer your question, Mr. Deji, first of all, remember I said there are two situations where you can have these machines already, you understand? But that's not always the case. In fact, in real world cases, you won't find that available. Do you remember?
Yes, 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 yes. Said
All
that.
right. Yes. So outside this now, other ways you can evaluate your clustering is the graph we saw. You can plot a graph to see how accurate this cluster was made. Now, for this situation now, there are cases where if the algorithm didn't cluster very well, you will find one of these greens, a data point from this green appearing here to these ones in blues. Or you have some blues occurring here closer to these grayish colors. That means the algorithm is not doing well. So another way to evaluate our clustering is through visualization. Do you understand now?
Yes, 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 I do.
All right. So, and there are other indications such as supervised learning has mean squared error, and what's it called? Yes, supervised learning linear regression has mean squared error, and logistic regression has its own, which is that should be matrix. A matrix. Yeah, there's a matrix evaluation for the model. The same with clustering. I think there's something called Shellowit score. There's something around that name. These are also ways you can evaluate a model. Okay.
Okay, okay. I'll read up on that silhouette score.
All
I'll
right.
read up on that.
All right. No problem. All right. So
Okay.
yeah, you're welcome. So we've come to the end of the meeting. So what I will encourage us is next week I'll try my best. I'll see how we can go through a few more slides, and hoping that within the week we'll be able to touch on this course, unsupervised learning course, and attempt to finish. Then we'll have our questions piled up, and once we're done with the practical case, because we'll be going through a live project. Once we are done with the live project, the real world project for the session, we'll now answer questions based on our self-learning. If there's any way you need more explanation, is the particular concept you need to be touched, you can come up and ask your questions. I believe that's fine. Please thumbs up if you prefer it this way. I can see only one thumb. That means the rest doesn't agree. Two persons only. Ibrahim, do you agree? Enoch, Christopher doesn't agree. Doba doesn't agree. Deborah doesn't. Esther doesn't. Mahmoud, Mba. Okay. No problem. All right. So see you next week, guys. Have a lovely weekend and see you on Saturday next week. Please, let's come prepared and well armored. All right. Good night, everyone.
Good night.
Yeah, good night. Good night, Femi.